In this project, we will simulate a two-dimensional wind tower using ANSYS Fluent software. In this project, the conjugate heat transfer of airflow in a simplified four-story building model applying wind tunnel is investigated. Turbulent airflow enters the domain from the top left region, and due to the heat transfer to air from the right diagonal wall with a temperature and heat generation rate of solar radiation equal to 305 Kelvin and 1000 watt per meter cubed, respectively, conjugate heat transfer leads to buoyancy effect, which helps the airflow exit the domain from the top right region. This process creates a steady airflow in all four stories of the building. The Boussinesq approximation is utilized to simulate upward force on fluid due to the difference in density. The present geometry is designed in ANSYS Design Modeler software and contains of a four-story building, an inlet, an outlet, and a radiation wall, which its purpose is to simulate the solar radiation energy. Also, the computational grid generated for this geometry is performed using ANSYS meshing software, and the mesh type is structured. Also, the element number is equal to 6375. Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, a new window will appear showing you the domain extents of your geometry. Also, under the View Length Units section, you can see the default geometry units, which is meter in this project. Also, under the Scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh is designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. Now there are several assumptions taken into account for this project. First, the type of our software is defined as pressure based. Second, we have selected the absolute formulation for velocity. And third, we have selected the steady time study since we didn't want our results to be a function of time. Also, since our geometry is in two-dimensional, we have selected the planar 2D space, and if you can remember, we talked about modeling the natural convection using the Boussinesq law. Therefore, we need to enable the gravity, and we set the value of it equal to minus 9.81 in y direction. Now if you expand the models and double click on the energy button, in the appeared box you can see we have enabled the energy equation since we wanted to calculate the temperature distribution inside our computational domain. Also, if you double click on the viscose button in the appeared window, you can see we have enabled the realizable K epsilon model since it is more accurate than the standard K epsilon. Also, as we talked about calculating the density changes due to the temperature change using the Boussinesq law, if you double click on the air under the fluid, under the material section, in the appeared window you can see in front of the density, we have changed it from constant to Boussinesq, and we have set its initial value equal to 1.225.
Now, if you click on the wind inlet boundary, you can see the type of this boundary is defined as velocity inlet. By clicking on Edit button, a new window will appear in which you can change the settings for this boundary. In the appeared window, in front of the velocity magnitude, you can see we have entered the value of 12 meters per second. Also, if you click on the thermal tab, you can set the temperature of this flow, which we have set it to 300 Kelvin. Now, if you click on the outlet boundary, you can see the type of this boundary is defined as pressure outlet. Again, by clicking on Edit button, we can further adjust the settings related to this boundary. Now, in this section, the most important point you should pay attention to is the gauge pressure, which has a value of 0 pascal, meaning that when our airflow enters our computational domain, it will exit it to the atmosphere. Now, if you click on each of these wall boundaries and click on their momentum tab, you can see a stationary wall motion along with no slip shear condition are defined for all of them. Now, if you click on the thermal tab for this wall boundary, you can see heat flux thermal condition is defined and the value of heat flux is defined as 0, meaning that this wall is adiabatic. Also, for the radiation wall, under its thermal tab, you can see temperature thermal condition is defined and its value is equal to 305 Kelvin. Also, we have a heat generation rate over this wall, which is equal to 1000 watt per meter cubed. Now, if you click on the thermal tab for this wall boundary, you can see heat flux thermal condition is defined and the value of heat flux is defined as 0, meaning that this wall is adiabatic. Now for this wall, you can see coupled thermal condition is selected. Coupled thermal condition means that this wall is in contact with fluid on its both sides.
After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order advent and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. After double-clicking on the Controls button, in the middle section of the software window, you can see that new part will appear. In the Appear part, you can see under relaxation factors for different parameters. Now these values are set here by the software automatically. You can change these values, which are between 0 and 1, by yourself for different projects you do. But it is highly recommended that you do not do that, since it may result in divergence.
There are two ways to check that your simulation process have reached convergence or not. Alongside checking the residuals reaching and nearing 0, you may define an arbitrary report or arbitrary boundary in order to calculate different parameters like pressure, velocity, temperature, and see whether they reach a constant value or not. If yes, it may be a sign that your simulation process have reached convergence. However, you must check the residuals as well. To create such report, you can simply right-click on Report Definitions, go over New, and select one of the options available based on your simulation.
After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the Initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software.
And finally, by double-clicking on the Run Calculations button in the middle section of the Fluent software under the Parameter section, we enter the value of number of iterations we want our solution to continue, and then by clicking on Calculate button, this process will start. Now, in order to extract 2D contours, we expand the Graphics section, go over Contours, right-click on it, and then select New. In the appeared window under the Contours of section, you can select your desired variable, which in this slide we have selected velocity. Under the Surfaces section, we deselect all the boundaries and then just simply click on Save or Display button. And now in this slide, you can easily see the velocity distribution inside our computational domain. The airflow will enter this 4-story building from the top left inlet and then will exit our computational domain through the top right outlet. Now we can simply extract another contour by changing the contours of section from velocity to temperature, for example, and then just like the previous one, we click on Save or Display button. And in this slide, you can easily see the temperature distribution inside our computational domain. You can easily see that the temperature of the radiation ball has increased in comparison with other regions. We can also extract velocity vectors by just right-clicking on Vectors and then selecting New. In the appeared window under the Vectors of section, we select the velocity, and again under the Surfaces, we deselect all the boundaries and then just click on Save or Display button. And now in this slide, you can easily see the velocity vectors of our airflow inside our computational domain. You can easily see the circulation of airflow inside each of the stories of the building due to the Bose-Einstein law and natural convection.
Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.